Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In the last video, we wrote a simple recursive algorithm to solve mazes, or at least to find the shortest path through a maze for us. And in this video, I want to animate them. So just seeing the algorithm, just writing the algorithm, it might not be exactly clear how it works. It can really help to actually have it drawn out for you. And we can kind of walk through what goes on here, but when we do it by hand, we can only take it so far. So our call started up here, and it said that the distance from here was going to be equal to, so this is inbounds, and it's not a wall, and it's not the end, because our end was down over here. So it said that it was going to be equal to the minimum of the return values of a step to the left, a step to the right, a step up, and a step down. Yeah, or maybe it was a step down and a step up. Order isn't really all that significant here. But when it steps to the left, well, this is out of bounds, so it would return, or so this is inside of a wall, so it would return a really big number. Then it steps here, this returns a really big number. And it would step down. Okay, well, then this is not a wall, and it's not out of bounds. So it would say, well, then the answer here is going to be the minimum of the four directions off of this plus 1. And that would go here, out of bounds, here, or here is a wall, here is out of bounds, go here, and then it steps here. This one steps here, steps here, steps here, steps here, steps here. And then it goes left in a wall. When it goes right, it would find the breadcrumb that we dropped down. When it goes down, it would find another wall. And when it goes up, it would say, oh, here's an empty space. So this one goes to the left, finds a wall. It goes to the right, and it's an empty space. So it goes to the left, finds the breadcrumb, goes to the right, finds a wall, goes down, would find another breadcrumb, and then goes up. Left is wall, wall, breadcrumb, up. Left is open, or sorry, right is open, 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 right is out of bounds, left is a breadcrumb, down. Out of bounds, wall, down. Out of bounds, goes here. Breadcrumb goes here. Breadcrumb, wall, wall, wall. So it returns a really big number plus 1. And this winds up checking there and returns a really big number plus 1. Then this one would, and we wind up walking all the way through here. Notice that everything that has happened so far, this entire path, is sitting on the call stack. Okay, and so when it gets here and it returns a 0, then this takes that 0 and the returns of the other values, which are going to be a really big number, takes the minimum of them, so 0, and adds 1. And it returns that 1 back to here, and that keeps going. So let's write code that can draw this out for us, at least the way in which things are explored. So to do that, we will put in some GUI code. So we'll import all of swing. Let's import color and import java.awt.geom._. Okay, so there's some imports for us. We can go ahead and create a panel. Panel equals new panel. I will override the paint. I'll set a preferred size on here. The size really doesn't matter too much. And then what's going to happen inside of here is this is supposed to run through all of the valid indices in our maze and draw little boxes for them. And it's going to draw the boxes with a different color based upon what numeric value is inside the box. So we'll start with writing a for loop. So, how about we'll call them I and j. So for I in maze.indices, j in maze sub I dot indices. And then I want to set the color. So let's do this this way. G dot set paint if maze sub I sub j is 0, then I set it to color dot white. Else, if maze sub I sub j is -1, then it will be color dot black. Else, color dot red. And the last thing we do is fill in a rectangle. And I will have this start at, we'll do a little bit of math here. So we will take I times the value of maze of I times size dot width divided by maze dot length. Yeah, that'll work. And then j times size dot height divided by maze sub I dot length, comma size dot width divided by maze dot length, comma size dot height divided by maze sub I dot length. Okay, we'll come back if we have errors there, and at the end here we'll make a new mainframe contents equals panel, open the frame. Now what we need to do inside of here is have it so that every time that we move to a new location, we'll do this every time we set down a breadcrumb, because this is where we're changing things. We will tell the panel to repaint, and to make this so that it is visible, we'll sleep our thread for 1/5 of a second. And let's see how many typos we have in that. Oh my gosh. Oh, I forgot to center it. Now one thing that you'll note about this is that this looks upside down, or at least inverted. Turns out that because of the values that I'm using for x and y, I'm drawing this as the transpose of what's actually in the text file, which not a big deal. I could certainly swap the I and j and draw it so that they matched. But of course it's the same maze. When you take the transpose, it just looks a little bit different to us. And we get our answer of 30. Let's go ahead and let's start from the top, make it so that it is centered so that you watching the video can see this. And you'll see that what it does here is it runs around the edge and it goes down every pot. Now you'll notice, like, after it filled that in, it immediately jumped back here. That's because I don't have anything, I don't have it redrawing when it's picking up its breadcrumbs. We could put in another repaint and sleep there if we wanted to. But this algorithm winds up testing every single path through the maze. And to make this clear, we can make a minor alteration to our maze. this will work. This should make it obvious. And I'm actually going to speed it up a little bit. Instead of sleeping for 200, I'm going to sleep for 20. So this should take 50 steps per second. And you can see what this is doing. So the alteration that I made was I opened a large space, an empty space inside of this maze. And you can see that what it winds up doing is running around inside of this empty space and tries every possible path inside of this empty space, even though the vast majority of them are total nonsense. They don't really take us anywhere, they don't add anything. And in fact, from the computer standpoint, turns out the worst thing that you could do would be to take out all the walls. Now, of course, for a human standpoint, if you give a human a 10 by 10 area where everything is blank and you ask them how many steps, they immediately say 19, because that's how many steps it would take. But the algorithm that we wrote here for the computer, it tries every single possibility. And it turns out that in this case, with a 10 by 10 maze, if I were to remove every single wall from this, it would never finish. Okay. Well, it would theoretically finish at some point, but not only will this video be over, but it would be a lot later than that. And so while this is running, we can actually do a brief estimate of, well, how long would it take? So in our 10 by 10 maze, we have 100 squares in here. Now the recursion technically branches 4 times at each step. Okay, so you could say that it goes to 4 raised to the power of the number of steps. But of course, most of the time, all 4 of those don't go anywhere. Only once do all 4 of them go anywhere. A lot of times, only 3 of them can keep going places, and then many times only 2 can, sometimes only 1. So we're going to reduce that and just say it's 2 to the power of the number of steps. So we kind of do a lower end of the estimate there. Then we're going to do an upper end on the fact that 100 is going to be equal to the number of steps, because at the maximum you can take 100 steps on this 10 by 10 maze. And so the question is, well, just how big is 2 to the 100? And so this is 2 to the 100, and you might recall that once again 2 to the 10 is roughly 10 to the 3, so this is roughly 10 raised to the 30. That's a big number. Well, how big is it? We're on a fast computer here, so let's say I wasn't animating this. Let's just say I was just brute forcing all the way through it, and my computer happens to run at a few gigahertz, and so I could do, maybe let's say I could take 1 step every billionth of a second. So I can take 1 billion steps every second. Well, then that would mean that it would take me 10 to the 21 seconds in order to finish this entire maze. Okay, well, that still sounds like a fairly large number, but of course seconds are really short. So another rule of thumb to keep in mind is that 1 year is roughly equal to 3 times 10 to the 7 seconds. It's about 31 million seconds in a year, but we're just taking a rough estimate here, only one significant figure. So let's divide that into here, and we get roughly 3 times 10 to the 13 years. For anyone who's up on their cosmology, that's a little bit longer than the current age of the universe. So in other words, if I were to take out all the walls, even on this simple little 10 by 10 maze, our current algorithm for solving it would take longer than the age of the universe in order to figure out the answer. And that's a bit problematic. So, in fact, over here you can see, even without me taking them all out, this algorithm is still wasting lots and lots of time exploring nonsensical space here. But that's because our algorithm, as it's written, tries every single possible path. Now there are some other algorithms. Instead of doing shortest path, maybe we want longest path, which is only a minor variation on what we have here. You wouldn't change much to make this a longest path. We'd be doing maxes instead of mins, for example, and we'd have to change the return values a little bit. Or what about counting all paths? Turns out those have to run through all the paths, and there really aren't any alternatives to that. But in the case of shortest path, there is. And so what we're going to do in the next video is we're going to look at how we might be able to optimize this approach just a little bit so that it doesn't spend quite so much time wandering around aimlessly in open mazes. Our current algorithm turns out to be actually pretty darn good as long as you don't open any broad spaces. As long as most of your open areas are just thin hallways and the few occasional possible turns. It'll work really well, even for fairly large mazes. So mazes that humans would find interesting, the algorithm we already have is good. But for something like this, where there's a big open space, it breaks down. And so we'll come back in the next video and we'll see how we might be able to improve upon this.